Here's one way to output a string of text from an ARM Cortex M microcontroller via the serial port. In this video I'm using an inexpensive yet powerful STM32 Blue Pill microcontroller. I'm only using the CMSIS Core library provided by ARM. I'm not using the hardware abstraction layer libraries available from ST Microelectronics, so the code should be applicable to any ARM Cortex M microcontroller regardless of which silicon vendor it came from. Let's fire up Kyle Microvision and create a new project. I'll give it a very descriptive name, Project 2. Okay, the microcontroller on the Blue Pill board is STM32F103C8T6. Here it is. And the software components that we're gonna want to include are the CMSIS Core library, and we'll want the startup code for this device, and that's it, nothing else. In the project tree we can see that the selected libraries are included, but we need to create a C file for add new item. We need to create a C file for our main function. Let's call it also project 2 add. Okay, and let's add the main function for our C application. It's just a regular C function, main function. There it is. In the reference manual we can see that serial port 1 is located on the advanced peripheral bus APB number 2. To transmit data on serial port 1, the microcontroller is using pin number 9 of the general purpose in-out port A. So the first thing that we're going to want to do is to enable the clock for the GPIOA. Here's how we do that in SystemCoreClock. First we'll build our project, then we'll include the relevant SystemCoreClock library. It's called STM32F10X.h. It's this one here, and then we'll reference the APB2 bus enable register of the reset and clock control structure provided by SystemCoreClock, and we'll modify the value stored in that register to turn the APB2 ENR IO to turn the port A on, to enable port A. Okay, that's it. The OR equals operator in C stores the value of this macro into this register without altering the values of any other bits in the register. It's very convenient. The RCC macro refers to the memory address of the RCC type def structure that's been cast to a pointer. Then we're going to want to set up pin number 9 for output. We'll configure the GPIOA-CRH control register high for that purpose. And we're gonna set it up for the alternate function in the push-pull configuration with the maximum output speed at the lowest value of 2 MHz. Here's how we write that code in SystemCoreClock. We'll reference the control register high of GPIOA, and we'll set it up with the following values. Control register high, configuration for pin number 9. We'll set bit 1 for push-pull, and control register high mode for pin 9. We'll also set bit 1 for the speed of 2 MHz. Okay, we've set up pin number 9 of GPIO-A to output mode push-pull alternate function at 2 MHz. Now let's turn the clock on for the serial port 1. It's on peripheral bus number 2. Enable register UART 1 enable. Now our serial port is turned on. The next order of business is to set the baud rate for communication. Let's declare an integer a 32-bit integer. Let's call it BaudRate. Now let's initialize it to 115200. This is one of the standard baud rates used in serial communication. Then we'll set the serial port 1 BRR register to this value. We'll take the SystemCoreClock provided to the serial port, and we'll divide that with the baud rate to get the divider value for the serial communication. Then let's set up the serial port for transmission. In this example, we don't want to receive any data, just to transmit. Serial port 1 CR1. TE is for transmission. And let's enable the serial port. And that takes care of the setup for transmission over the serial port 1. We're now ready to send a string of characters over our serial port. For that purpose, we'll use the data register. Data register DR. And we'll put a value of a string. Let's name it str into this register. That's how we send a string out via the serial port. Let's declare and initialize this string. In C language, a string is an array of characters that is terminated by a null ASCII character. So we're declaring here an array of characters, and let's put a value in it. Hello world. The data register will process one character at a time, so we'll need to set up a loop that will cycle through all of the elements of the array. Let's set up a while loop. We'll have some condition here. In C language, the name of the string is a pointer to the first element of that array. Every string is terminated by a null value. So the while loop will cycle through all of the elements of the array until it reaches the termination of that array, which is the null ASCII character. We're going to want to increment this pointer after every execution. And of course we'll need a counter. We'll need a counter in order to reference each individual element of the array. And of course we'll need to increment that counter after each execution. Let's save and compile this application. Here's what my setup looks like. In order to upload the application into the microcontroller, we'll need to set up the programmer. Go to Flash Tools, Debug tab, and then the programmer that I'm using is an ST-Link dongle, but I've upgraded the firmware to J-Link, so it's actually a J-Link. Go to Settings, Set. Okay, make sure that the communication method specified here is single wire SW. Everything else looks fine. And now we're ready to flash. Hit the load button. Everything seems fine. To view the output from the microcontroller, you can use any serial terminal software. I'm using PuTTY. I've got an FTDI serial interface connected to COM port number 7 on my computer, and the baud rate that we specified in our application was 115200. Yes. When I hit the reset button on the microcontroller, here you go, one, again, we should get the whole hello world string displayed in our terminal window. Unfortunately, we only get the very last character, the exclamation mark. Now, why is that so? The serial port on our microcontroller has a buffer, and that buffer is being stuffed with data from the data register at a much faster rate than it's able to handle. So if we want to see the entire string, we need to slow down that rate of transfer. Let's run a for loop after each character. That'll keep the processor busy, and it will effectively slow down the rate of transfer. For integer, let's call it j equal to 0, and let's run this loop 10,000 cycles. We don't really want it to do anything, just keep the processor busy for a while. So this is good. Let's save, rebuild, and reflash. Okay. Let's see now what the output looks like in the terminal window. I'll hit the reset button again, and we get the entire string. Here, I'll do it again. Hello world. This method works, but it's not very elegant. There's a better way to do this. Instead of running the for loop, we can check to see if the serial port buffer is empty before we send out each character. To do this, we examine the contents of the status register to see if the TxC bit is set. If UART1 status register status register bit TxE, if that bit is set. If the TXC pin is set, that means that the buffer is empty and available, and we can transfer another character for processing. If, however, the buffer is not available, it's not empty, then we're going to want to repeat this process until the buffer does become available. This method is much more elegant. Let's save, recompile, 0 errors, 0 warnings, and let's reflash. Let's check and see if the program works. I'll hit the reset button. It works fine. It works perfectly. Finally, we can make this procedure a separate function. Instead of putting it in the main function, let's make a new function. We'll call it void transmit string, and we'll take one argument. That argument will be a pointer to our string. We should declare this function before we use it. Void TxString enter. Our application needs to have the main function, so let's create it. Integer main void okay. We want the declaration, we'll declare the string and initialize it in the main function. Let's call it string1 to avoid any confusion, and then we'll pass it on to the transmit string function for transmission out of the serial port of the microcontroller. str1 good. But why settle at one string? Let's send out two strings. We can define another string. Let's call it string2. The contents of that string will be testing 0, 1, 2, 3. And we'll pass that string to our function as well, string2. We can do that. We can create a new string, string2, or we can replace the contents of the original string, string1. To do that, we can use the string copy function, strcpy, and in order to use this function we'll need to include the standard string library, string.h. So string copy str1, comma, replace content of the original string. So a space here as well. Let's not forget to close the parentheses, and then let's save, recompile, and reflash the application. I forgot to pass the revised string1 to the TxString function. So let's do that. String1, and then once again let's save, recompile, reflash. What does the output look like in the serial terminal? Let's take a look. I'll push the reset button. Once again. Once again. Perfect. One last thing I would like to point out. Please note that the while loop does not terminate when it encounters a 0 character. That is because a 0 character, the ASCII code, the ASCII code of the 0 character is not 0, it's something else. So therefore it's not false, and the while loop will keep running. Well, thank you for taking the time to view this brief video. I hope you've enjoyed it.